Hey there, welcome back to CMTEQ channel where we make power system practical and easy to understand. In this tutorial, we're going to be diving into one of the most important safety studies in electrical engineering. That is none other than the arc flash analysis, and we're going to do a quick demonstration over here in DIgSILENT PowerFactory, as you can see. Great stuff. Now, there are three key takeaways in this tutorial. Number one, why do we perform this type of analysis in power system? And number two, how to set it up in DIgSILENT PowerFactory. Basically, how to set up your power system network to perform an arc flash analysis. And lastly, how to interpret the result of your arc flash analysis. Basically, we're going to dive into the output like the incident energy, the arc flash boundary, and your PPE level. So if you want to improve your power system understanding of this topic, make sure you stay until the end of this tutorial. Now, without any further ado, let's get started. Now, let's answer our first question of the day. Why do we perform an arc flash analysis? Now, to answer that, let's first run a quick short circuit analysis on our bus bar here. There we go. Now, we can see that we've got about 43.7 kiloamps of short circuit current on this bus bar. Now, the issue here is that when a short circuit current, a short circuit occur on the switchboard or in a substation, what will happen? You're going to get a plasma arc that basically can form between the two energized conductors, as we can see in this beautiful representation here. Now, the problem here is that this arc can reach up to 20,000 degrees, right, of radiant heat. Okay, now if you want to compare it, theoretically this is hotter than the surface of the sun. And what's the result of this? There will be extreme heat, pressure, and light that can cause severe burns in no time, basically in milliseconds, and also cause destruction to substation equipment, right, because of the level of the heat. So in power system studies, we perform the arc flash analysis to basically quantify the level of this heat so that we can take appropriate measure. I mean, just like in short circuit analysis, you run it so that you can specify your circuit breakers rating, right? The same applies to arc flash analysis. We perform it so that we can quantify the problem we will be dealing with in case it happens. And the result of this analysis will basically tell us how much thermal energy can reach the workers, the power system technicians, at a given distance, and how far they basically need to stand, basically the safest distance, while they're performing their work or in a situation where there is an arc flash that occur, to basically stay safe. In short, it's all about protecting the technician, the power system engineers, and obviously the equipment at the substation level. And the applications of arc flash analysis basically applies everywhere. In substation, that's obvious. In industrial plants or switchboards, in hospitals, data centers, basically everywhere where there's power and safety is very critical. That's where you need to apply these studies of arc flash analysis so that you can determine obviously the incident energy, but that's not the only thing. We also need to know when it's safe to re-energize switch gears after maintenance or after a failure, whether you can safely close the circuit breaker again to allow power to circulate, all right, and the safe distance that workers can operate. So protection, coordination, there is a lot of things that these arc flash analysis can inform us in terms of ensuring that there is reliability and continuity of supplies as one of the main requirements of power systems protection. Great stuff. Now, let's now move on to see how we can set up arc flash analysis in DIgSILENT in this small network with just two bus bars. But mind you, the settings, basically the method how you're gonna do it here will applies in any network, whether big or small. Now, to perform an arc flash analysis in DIgSILENT, you just need to make sure you've got a properly configured network, small or big, right? And just ensure that your network is able to execute load flow analysis, and you need to run a short circuit analysis like we've done here. That is because the arc flash analysis depends on the short circuit current, so that it can compute the calculations of the incident energies and the distances that the output result that you're going to get from the analysis. So if you can't perform a short circuit analysis, then you're not going to move forward and compute your arc flash study. So you must configure your bus bar and your lines, your transformers correctly, so that it can give you the correct short circuit analysis, short circuit current for your network. That way your arc flash analysis is going to be based on the correct variables. I've already said earlier, this is 132, this is a 32 kilovolt. Let's just double check here. Okay, so this is a 33 kilovolt bus bar. Now mind you, if we run this short circuit at this point here, and this is what, 11.6 kiloamps of current. Now even though this bus bar have a lower short circuit current compared to the 43 here, but because of the distances right between the conductors that are gonna be energized to cause an arc, you might get a higher incident energy compared to this point here, which means your PPE level might be higher than here. I'm just saying, but we're going to discover that in a moment. So make sure you apply the distances correctly, as we're going to see now. So let's go ahead and double click on the bus bar, and we're going to move over here to protection, and we're going to enable the arc flash analysis accessible location, and these are the parameters that we need to fill in. You need to check the standard that is IEEE 1584, that basically define these conductor gaps, or the distances between conductors at different voltage levels. Okay, so you have to input in the correct parameters so that your result can also be correct. So we're going to go ahead and enter 250 millimeter here, and the distance factor for open air, we're going to leave it at 1. The working distance, this is very important, crucial, and we're going to set this as 910 millimeter. Great. Okay, then we're going to move on to the next bus bar here, and protection is already selected. We're going to enable accessible location, and over here now we are now at a lower potential, 132 kilovolt. So the conductor gap here is obviously much lower, and that is going to be 32 millimeters. The distance factor, we can change it to 0.5, and the working distance is also going to be much lower at 33 kilovolts. So let's go ahead and say 4.455 millimeters, and we are also working with open air, so our distance factor will be 0.5. Now we're not going to go through the detailed specification, but these are all defined under the standard, the IEEE standard that deals with these parameters. Then we're gonna say okay. Great. Now, by the way, if you find this tutorial useful, informative, please make sure you give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. You are also more than welcome to share it to your social media network. That is the best way to support CMTEQ channel. Thank you so very much for the support. Great. Now we basically ready to execute the arc flash analysis. This is the icon that we need to click on. Now, if you do not see this icon, you simply need to enable protection here. The icon should pop up. Okay, and then you're gonna click on it. As you can see, we already have the method selected for us. This is a default DIgSILENT settings according to the IEEE 1584 that define all the parameters that we've set for these bus bars. Now, the IEEE 1584-2018 is an international standard for arc flash calculations, which basically uses empirical formulas based on laboratory testing to predict the three output results that we are chasing here, which are the arc flash current, which is basically your short circuit current, your incident energies that is measured in joule per centimeter square, and your arc flash boundaries, okay, so that we can determine how far can the person safely stand when they are exposed to an arc flash occurrence, okay. And when they were doing these calculations, they were considering the system voltage. Now we've defined our distances here based on the two types of system voltage here. They take account of the system voltage, the fault current, that's why we had to run the short circuit calculation first, the equipment types, the conductor gap, working distance, and obviously the type of enclosure, whether it is open air or box in an enclosure. So basically by selecting this method, PowerFactory automatically behind the scenes, right, it basically will calculate the incident energy, arc flash boundaries that are compliant with also the NFPA 70E standard, okay, giving us reliable safety informations about our power system network. Great stuff. Now let's go ahead and execute our arc flash analysis. Execute. There we go. We've got our result here summarized already for us, okay. But over here on our network, the result boxes are empty for us. Now this is very crucial. We need to know what's going on here. Although we can see on the grid bus bar and the load bus bar, we already have our incident energy, the PPE category. Now it's not showing, it's not applicable here. Now this is a problem. So we need to define here the variable so that we can see what we've been chasing on. So I'm going to click on edit format for short circuit node, double click over here. We are already under arc flash analysis. Now we've been chasing these guys here, the arcing current, the arc energy, the incident energy. Now I'm gonna click the arcing current, which is basically the short circuit current. I'm going to click on the incident energy, the distance, the boundary, the safety distance here, the PPE category, basically the required personal protective equipment based on your arc flash or incident energy levels that you're going to get as per your analysis. So we're gonna say okay, and we just need to enable everything here because we clearly do not want to leave any informations out of our side, including the unit. Okay, great stuff. Now as you can see here, based on the result, the incident energy obviously is 398 on this bus bar and 1493 on this bus bar. Now the PPE, very interesting, the same on both levels. I'm going to stop this tutorial here. On the next tutorial, we're going to dive deep into understanding these results here, interpreting what's going on here, because I'm going to show you something here quickly. If we click on this bus bar, okay, and we change here, let's say 1200, okay, you can even change it to boxed, right? And then you say okay. Then let's close here and we run it again, okay, and you're going to see that it changes. Okay, now we are on category 3 while this is still on category 1. Now obviously the coloring, they are defined here. You can see the colors based on the incident energy levels that you are working on. And if I click on my transformer, because remember the transformer here is the one dictating the short circuit at this node here. Now we know that this bus bar is sitting at 11.6 kiloamp of short circuit current, and that is informed by the short circuit impedance of this transformer, which is at 3%. Now if I change this to 1, right, for the 0 sequence, and a positive sequence, and we say okay. Now we close here, we execute this again, right? And we're going to see that this is category now back to 4, or changes to 4, and this one stays to 1, because we now tempering the short circuit parameters and the connection, the working distance on this bus bar. So it changes your incident energy. So in the next tutorial, we're going to dive deeper into understanding and interpreting our result. So stay tuned for that next tutorial. And if you find this tutorial useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. Until next time, cheers.